Hello, welcome to the class again, and finally we'll start to see some vision applications of all the math that we studied on rotations and translations. So in this lecture we're going to study dynamic perspective. The question is, what happens when a camera moves? A moving camera gives us a lot more information than a static camera. It gives us information about depth in the scene, and it reveals what the so-called ego motion is. Ego means I, so therefore ego motion means the movement of the camera. So let's proceed. So let me remind you of the pinhole camera. We studied this in earlier lectures. So there is some object out in the world, and that projects to an image, and we have the standard equations of perspective projection. We derived them earlier, but I will in fact consider simpler versions of those, where first of all we get rid of the negative sign, and then secondly we can as well assume that f is equal to 1. Assume f is equal to 1, and why is that allowed? We can just measure everything in units of focal length. So then the equations will become x equals uppercase x divided by z, and little y is uppercase y divided by z. So those are straightforward, simplified versions of the equations for pinhole camera, the pinhole camera model of perspective projection. Okay, so what happens when the camera moves with respect to the world? So when a point x, y, z in the world moves relative to the camera, its projection in the image, which we use lowercase letters for x, y, moves as well. This movement in the image plane is called optical flow. So suppose that the point xy moves to the point x plus delta xy plus delta y in time delta t, then we can divide delta x by delta t, and that's considered the x component of the optical flow, and we can divide delta y by delta t, and that's considered the y component of the optical flow. So the optical flow is a vector. It's a two-dimensional vector, and at every point xy in the image. So let's take an example. So the example that I'm showing here is that due to J.J. Gibson. Gibson was a psychologist who emphasized the importance of optical flow for visual perception. So in this diagram, what you see is the optical flow for a pilot landing a plane. So when a pilot is trying to land the plane, let's say this is where he's going to land, and what you see here is the runway. What the pilot will see as he or she approaches the runway is that the various points on the ground will appear as if they are streaming out. It's the same sensation that you get when you're driving through a tunnel. And these vectors, these are these two-dimensional vectors. Each of these vectors is the u, v. The x component is u and the y component is v. And these obviously are functions of xy, because at a location here they point outwards and to the right, at a location here they point outwards and to the left, and so forth. So that's why we use the term vector field, because we have a vector at every point, and as a function of x and y, the vector can vary from point to point. Let's take up another example, also due to Gibson. This is what the optical flow field looks like from the side window of a car. So imagine that you're driving on a highway and you're looking out from the side. So all these vectors here correspond to the optical flow, and that's pretty straightforward. Notice that the vectors are of differing lengths. So these vectors are big and the vectors here are small. Well, why is that? Well, that corresponds to the fact that those points are far away. The environment is not moving, the ground is not moving. What's moving is the car. So the relative velocity is is given by the fact that if the car is moving at some translational velocity t, the ground is moving relative to it at minus t. So all the points on the ground undergo the same movement, but there are some points which are nearer to you. Those will give rise to bigger optical flow vectors, and there are points which are far away, and those will cause small optical flow vectors. But this example directly tells you that we have some information here to tell us about the depth, because essentially the smaller optical flow vectors correspond to large z, and we'll be able to figure this out exactly mathematically in a few slides. So let me tell you the outline of what we'll do in the next few slides. So first of all, we are going to derive an equation which relates the optical flow field to the scene depth and the motion of the camera. So this is the fundamental equation of optical flow, and we will do this by simple geometrical analysis, and this analysis will exploit the representation of rigid body motion as some combination of translation and rotation. After we have done that, we are going to try to make sense of this. We are going to try to interpret this and get some physical intuition. And basically what we will find is that the translational component of the optical flow is the more important one, and that reveals something about z, the depth, as well as the translational vector t. The rotational component of the flow field is also important, but less so. Its main purpose is to tell us something about ego motion. It tells us about how the camera is rotating. It doesn't tell us anything about the scene. So we'll try to understand that as well. It will fall out more or less straightforwardly from the equations. So let's get down to business. Our goal is going to be to derive the equation which relates the optical flow field to scene depth z of xy and the motion of the camera t omega. Okay, so let's get going. How does a point x, and note that I always use uppercase quantities for scene variables, how does a point x in the scene move? So we are going to give the movement to the camera. So assume that the camera has a translational velocity which has three components, t sub x, t sub y, t sub y, comma t sub z, and an angular velocity which is given by the components of omega. How do I characterize the movement of a point in the scene? The movement of a point in the scene is equal and opposite to the movement of the camera. So the camera's movement is given by t and omega. So in the scene, so points in the scene will appear to move equal and opposite. So we have a translational term and a rotational term given here, and the minus signs are because the camera is moving and we consider movement of some point in the scene. And x dot here is essentially the standard notation for temporal derivative, where x is a vector, dx upon dt is given by x dot. Okay, so once we have this vector equation, 3.1 in this notation, I can write it out in coordinates. And this is just working out this vector product term, and if you do that, you should get this expression. So this is quite straightforward. And now we have expressed the movement of a point in the scene in terms of how the x coordinate changes, how the y coordinate changes, and how the z coordinate changes, using the information about the translational vector. And here this x, y, and z correspond to sort of the scene coordinates. Okay, I should perhaps have used uppercase for x, y, and z here because these are meant to be scene coordinates. Okay, so now we are going to consider the effect of projection. So far, in fact, we had no notion of perspective projection. It was just the camera is some object moving, and then we have described relative movement as a combination of translation and rotation. So the equations of perspective projection are given here. So the only little trick here is that I assumed f is equal to 1. This is not a big deal. I'm just saying that instead of measuring in centimeters or meters, I measure length in units of focal length. This is a kind of trick that physicists use all the time. If I want to, I could actually have the f in there and carry through the equations. In any case, it's not a big deal. So what we have to do is to take the derivative. So if I have little x equals uppercase X upon z, I have to now take the derivative of this with respect to time. So now we have this standard formula. So how do I take the derivative of a fraction where x is the numerator and z is the denominator? Well, we take the denominator gets squared, and we get x dot z minus z dot x. So this is standard calculus, right? Calculus with the derivative of the ratio of two functions. So that's what will give us this expression right here, and I'll get a similar expression for y dot. So this is totally straightforward. So this is just a consequence of calculus. We are considering how the little x, how the image plane projection little x and the image plane projection little y, how that changes when I with time. And these here I should really have uppercase y and z should have been used. So this is an error in my slide. I've used lowercase quantities here, but these should all have been uppercase because these are seen quantities. Okay. So let's move right along. So now what we have to do is to plug in expressions for the temporal derivatives of x and y and so forth from the expression here. So that's what I do. So let's say I take this equation, and then x dot, I plug in x dot from here, and I plug in z dot from here, and that will give me little x dot. And then I can simplify a little bit using the fact that little x is x upon z and little y is y over z. So I'm going to not go through the algebra for you here, but you should sit down and verify it, and you should be able to work out this equation. So please verify this. It's just calculation, but it's worth doing. So we have now got an expression. This is the grand equation that I'm interested in, and I'm going to rewrite it so that you can see this. Let's get the intuition right again. So what is x dot and y dot? So this is, as always, x dot means d sub x upon dt, and y dot means dy upon dt. So these are the two components of optical flow, respectively the x component and the y component. And what we did over the previous slide was to derive a relationship between these guys and movement in the scene. And the movement in the scene has a translation component and a rotation component, and then we have little x, little y. These are just coordinates in the image plane, and then we have this fellow z, and z is in general actually going to be a function of little x and little y, and this is of course depth in the scene. So what do we observe? We observe that the translational component has a dependence on depth. So this guy is going to tell us something about scene depth. The rotation component has no dependence on z. So what the rotation component does is it just tells us about rotation.